Ladies and gentlemen, this is one of 4 test pools in Central Florida that we've evaluated over the past decade. So these kind of complement the work we've done up at our Lenox, Massachusetts test facility. The difference being these are all conductive in-ground pools, because we wanted to be able to answer the question, is a conductive in-ground pool similar to a vinyl-lined pool? And if not, what are the differences? The key takeaway is they're not significantly different, and what you'll find is that when you don't have the equipotential grid around the perimeter of the pool, you're going to get unacceptable voltage levels. So what you're going to see in the videos are different representations of the tests we did at different voltage levels. So one of the tests is at 14 volts, and we did that for the NEC code making panel, the expert committee that the standards board directed to come back to them with some recommendations that ended up in that new TIA for Article 680.26, which now requires either a steel mesh or a copper mesh, one of the two, around these swimming pools. The testing at that point was at 14 volts, and what we were finding is almost 7 volts along the back area where we only had the single bonding conductor. And then we elevated the voltage up to 40 volts, and we did the testing again, and we were seeing upwards of 20 volts, 17 to 20 volts in that test. And then when we went to full line voltage and we could get about 97 volts on the water, we were literally seeing 50 to 60 volts back here, which is fibrillation levels for a swimmer that's immersed up to their chest in the water with their arms out on the deck. So we're going to walk through what it looks like underneath where you can't see, because in the tests you won't be able to see this, which is the equipotential grid that I laid on top of where the grid that's actually been put in is beneath the deck. And you won't be able to see in the tests that bonding wire, that single number 8 bonding wire that runs along the back and just runs every place that we couldn't get an equipotential grid. But I'll show you the real grid. There it is. You can see it. It's about, I'm going to say 10 inches down, maybe 8 inches down. And if you notice, it's actually connected to the bonding wire. So that's this thing, but underneath it's connected to the bonding wire, and it goes around the back of the pool where there just wasn't enough real estate to get in the grid. So during the test, that's what you should keep in mind, is this is what we're looking at below ground. Now, before we splice in the actual videos that were taken this past weekend, and possibly the one from the code making panel work a couple of years ago, what I'd like to do is just show you a couple of other nuances with this. So one of them is when we look in here and we get down there on that where the connection is to the copper wire that runs around the back, it actually is in the footer. So they laid it out there, it got inspected, and then they pour concrete. So there's like a concrete footer along the base of that screen. And then if we go over to the other side, let me take, this is an easier way to see what's down there with that. So again, right where I'm pointing, we would see that connection to the bonding wire. And then you got a couple of other nuances here. For example, this here, this pigtail comes up from the rebar that forms the pool shell, and then it goes over and it connects to the rebar in that footer, and that's all connected to the bonding wires and in this case to the equipotential grid that also happens to be along this side. So we've got full conductivity on the water when we energize the bonding system. And to energize the bonding system, what we do is we come out here to where this is generally connected to the screen. There's where it connects to the screen right down there. And this wire this wire right here, which one is it? This one. This wire right here, when we disconnect these, we can actually electrify that, and when we electrify it, we get that 14 volts or that 40 volts or the 96 volts, which is a full line fault. We get that right on the water itself. So then we can measure between the water and the deck anywhere we want along here and see whether or not the voltage is unacceptable or acceptable. So as you watch these, what we'll find is that on top of the equipotential grid, things are safe, just a few volts or less than a few volts, and back along where there's just a single wire is, that wire just isn't adequate enough to get a voltage potential on the surface that's equivalent to the water. So we see some serious voltages. The other thing I will point out is as we get further out on this grid, since it's literally 8 to 10 inches deep, the voltage equipotential capability of it tails off, so it just doesn't perform well out towards the edge. Performs really well in here along the along the inside and along the bonding beam for the pool, but it doesn't perform that well as you get out. I'd like to see something a little further out, but this is what we have. So let's go to the test. So what I'm going to start with is just a voltage measurement here about 1.5 feet away, and you can see 55 volts, 56 volts on the water, and we are right there at the I'll say maybe 1.5 feet out. And we'll come down to this end and do the same measurement, and we're at 52 volts, 53 volts over here. Here's 55, 56 volts out here. Drops to 51 when I'm not stepping on it. Anyway, over 50 volts. Significant. So let's go over here to where the grid is. Got the equipotential grid here, and we'll get about that 1.5 feet out. And we got 1.5 volts. We'll move it over a little bit. 1.45 volts. Over a little bit more, 1.3 volts. Out a little bit, 1.9 volts. Now we're right at the edge, about at the 3 foot mark. I'm going to say the 3 foot mark is probably right here. So I would expect that anything out here, yep, it's getting higher. If we get out a little further, it gets even higher. So once we get off of that grid, you can see significant voltages. Take away from this is the equipotential grid does a pretty decent job, keeps the voltage around 1.5, 2 volts during a full line fault. Now let's see what we actually measured full line fault wise. So I'm going to grab my meter out of the water here. And we will take this and we'll go over to where we put the line fault on the water. Let's see what that 120 volt fault looks like when we put it on the water. How much got to the water out of that 120 volts. We expect some voltage drop. This isn't a clean conductor and a load center, so we'll put that in the water. And over here at our meter, we're measuring the line voltage, and it's 96 volts. All right, 96.1 volts. Just to take you through why it's not 120, it's because we're putting that fault on the water, and we're putting it on the full surface area of the pool. The voltage dropped from 120 to 96, but there's 96 volts on the water, and of that 96, over 50 volts got between the water and the deck, which means that a swimmer could certainly be either fibrillated or seriously injured, but we would definitely have some kind of serious issue with just a single bare copper number 8. And this is at a fully compliant Florida swimming pool that's been inspected, approved, and was built to code. when that code required only the single bare copper wire. And then you can see what happened where I actually came in after it was built to code and added the equipotential grid. That's that 1 foot squares equipotential grid.